In part 5 of this series, Are We Alone in the Universe? We're going through again astrobiology. And our main question here is life beyond the solar system. So before we've been looking at, looking for life in our own solar system, so planets around the sun or even moons of some of those planets. But now we're going to set our sights a little bit further out. So now we're going to be looking at places that are not around the sun. So we're going to be looking at what exoplanets are, and then we're going to look at how we actually detect them. So there's various techniques, and I'm going to go through a few of them with you because they're really interesting, I think. And then we're going to go through the results so far. This is so interesting because this is a very dynamic field. This stuff right here is changing all the time. I mean, this right here is really exciting, I think at least. So this right here is changing all the time. There's always new updates being made, which I think is really cool. So let's take a look at this. First of all, what is an exoplanet? Well, an exoplanet is just a planet around another star. Now, a lot of the pictures that I'm going to show you are no longer going to be real pictures. See, in a lot of the other videos, I was showing you real pictures, but these are going to be diagrams. Whenever it's a real picture, I'll tell you, but for the most part, these are going to be artists' conceptions of what these things might look like. So, for example, this is a drawing. This is an artist's idea of what a planet might look like around another star. Now, it's not completely made up. There are a lot of facts behind why we think different planets look the way they do, but we're going to talk about that. So first of all, what an exoplanet is, when we say that it's a planet around another star, we mean a star not our sun. That's the main thing that we mean. So not around the sun. Not around our own sun. Okay, there are lots of other suns out there, lots of other stars. So if it's a planet going around another star, then we call it an exoplanet. Now, do planets have to be around other stars? No. There are things called rogue planets. So they do exist, but they're really hard to detect. So we're going to start by detecting the easier ones, which is the planets around other stars. At least we know where to look. Look in the sky. If you see a star, then look around it, and maybe you can find planets around it. Right? Because, of course, you can look between stars. There might be a little planet floating along. You just might not see it. It's too faint. It's too far away. So we're going to focus our efforts on exoplanets, planets around other stars. Now, these planets, what's kind of interesting is that up until 1995, or even maybe earlier, some people say it was in 1992. It depends on when you count the first exoplanet. But up until 1995, the entire list of known planets in the universe was just confined to our own solar system. So around our own sun, when we had the 9 and now what we call 8 planets, that was the entire list of for sure confirmed planets. Now, we expected the existence of other ones. And that's because our own theories about how stars form from hydrogen gas. So this is the theory. We talked about this in another video. So if there's hydrogen gases that are being compressed to such sufficiently high pressures and densities to where they can actually start nuclear fusion, and all the leftover material from that, not all of it's used for the star, so some of it might actually start to sort of rotate, and those pieces might form together and might actually clump together gravitationally. And those pieces then clear out other spaces around them, and you end up with this right here, a solar system, SS for short here. You end up with a solar system like this. That's a system around a star, like our own. For example, we have Jupiter and Saturn, and we're the third one from the sun here. So this is what we thought. And so we thought, well, most stars are predicted to form along with planets. So we expected the existence of other planets around other stars, but we weren't sure, not until 1992 for a pulsar planet, or 1995 for a planet around a main sequence, sort of a regular star like this. So that's why I'm going to consider 1995 the first one. So this right here, this will be the first confirmed exoplanet. And just to be safe, I'm going to say around a normal star, because they did detect something around another weirdo star. We're going to talk about those a little bit later. But for right now, a normal star, what we call main sequence. So what we imagine as a star. So 1995 only, which is really recent. So before then, we thought they would exist, but we weren't sure. Now we know. And we're detecting more all the time. So now, why are they so difficult to detect? Why did it take until 1995 in order to actually find them? Well, you have to think about this. You have a star, right? So let's say this right here, let's just say is the sun. And around it, let's say you have a little planet orbiting around here. Now this little planet, it doesn't give off much light. In fact, it gives off almost none. What it does, it reflects light. The thing that's actually giving off light is the star. It's super bright compared to the planet especially. So if you're trying to see planets around other stars that are super far away, while the star is so bright, the planet is just too faint, it's too dim, you can't actually take a picture of it, at least not easily. It's exceedingly difficult. So that's why it took until just very recently for humans to even have the technology to detect them. So that's the main reason why it is difficult to actually detect them. So it's not a simple process at all. It's not like just taking a regular picture, not at all. Now, when we have exoplanets, we've started finding them. Let's talk about, first of all, some of the way that we actually name planets themselves. Some of them are based on mythology. So, for example, our own planets, the planets that we know around our own solar system, those are based on Greek mythology, so things like Mars and Mercury. These are all characters in Greek mythology, Venus, etc. So these here, those might be names that we could use. But the problem is, if we use mythology, I mean, there are expected to be billions of exoplanets, so there aren't billions of characters in mythology. So we maybe need a better way to name them. So what the main convention is now, we normally name them after the star name. Now, the stars don't always have very easy names. I mean, some of them are named really cool things like Vega and Sirius and Pollux and Castor, and they've got really cool names like Betelgeuse. And again, some of those have, historical names. But a lot of them are just based on a catalog. So just when they're actually trying to name it, whoever does the catalog, well, they just name them based on which stars they found. So for example, there is a star named HD. That's named for the catalog. And it's 20945. How does it go again? With an 8, I think it is. Let's just see. So 2094558. Yes, that is the name of the star. And what we do is we add a little B to it. So this right here, this tells us that's the star. And then this little B right here, that tells us it's the planet. Now, what if we found another one around star HD 209458? Then the next planet will be called C, and the next one will be D, and then E, and then F, and so on. So that's the main way we normally name stars. We name planets around other stars. We name them based on the star, and we just add a little B to it. Now, sometimes they're also named after the search project's name or the catalog. So, for example, we might have one, there's really funny names. One's actually called OGLE, O-G-L-E. That's actually a gravitational lensing survey. But there's lots of other ones. There's one called Kepler, which we're going to talk more about. There's one called HARPS, for example. There's, Super WASP. There's a whole ton of these. This stands for the Wide Angle Survey of Planets, I think it is. There's a French one called CORUT. So anyway, there's lots of these surveys trying to look for exoplanets. So they have different names. So for example, you might see in a catalog, there's a planet called Kepler 22b. Then you'll know, it's from the Kepler project, and B means it's a planet. And if it's Kepler 22c, then you know, hey, Kepler 22, that star has 2 planets at least, because there's a B and a C, and so on. So that's normally how we name them. So just so you can sort of see how we actually do this. Now, how do we actually detect them? Well, directly detecting them is super hard. And when I mean directly detecting, I mean you actually image them. We call this direct imaging. So what I mean by this, you take a picture. You actually take a picture and you see the planet. This is unbelievably difficult to do because the stars themselves are millions of times brighter than the little planet. So that would be like trying to take a picture of, like the sun, with like a little firefly that's right beside it. Of course, the sun would completely wash out the image. So imaging them directly is exceedingly difficult. We're just starting to figure this one here out. But indirectly doing them, that's a bit more well known. And so we're going to talk about some methods like the Doppler method and the transit method. Now, and what I mean by indirectly is that here we look at, so here's the main thing that we do here. We look at the star's light. And by looking at what the star's light is doing, we can infer, in other words, we can guess the existence of planets. So what we do is we watch the star very carefully, and by looking at what the star's light is doing, and I'll go over this in more detail of some of these ones, like Doppler method and transit method. But we look at the star's light really carefully, and we infer, in other words, we detect that a planet must exist based on what it's doing to the star's light. So these are two such indirect methods. Now there are lots of other methods. One of them is called gravitational lensing. That one is really cool and worth looking up. Other things like transit timing and astrometry. So there's a lot of other ones as well, but these are sort of the most well-known ones, especially Doppler method and transit are probably the two biggest, most well-known ones. That's why I'm going to talk about those. So in following videos, I'm going to focus on the two different methods here, on the Doppler method and the transit method. And after that, we're going to talk a little bit about the direct method. And after that, we're going to go on to what some of the results are.